Start now.
Okay, let me share my screen. Please confirm it's visible.
Yes, sir. It is visible, sir.
Okay, yeah, okay, so thank you.
Sir, your video is not visible, sir.
Yeah, so video is basically then, yeah, what happened in last time also, people streaming issues were there in the video. Anyway,
Okay.
I think there is some issue.
Okay, okay, sir. You can continue, sir.
Yeah, there are some few issues there. Okay, okay. Good afternoon to all who has joined here for this course, and today we are going to talk about the design of materialistic algorithm. Most of you already attended few lectures on materialistic algorithms, different types of materialistic algorithms. But today lecture, what we plan is we try to see that what is common there, what are the common features which are available in most of them, and if you want to design a new materialistic, how you can design it, and likewise. So this talk is mainly on for that purpose only. Okay, let me take a laser pointer. So why optimization? We discussed a lot on that because of we need in day-to-day exercises, day-to-day work which we are doing, or solving certain kind of maybe industry problems or in academia problems or research problems, or nowadays very popular tuning the parameters or developing a models for machine learning, or some kind of other kind of industry problems, and at the micro level also schedule tasking in the computers. So you can see other applications are enormous, and because of this wide variety of these applications or problems, if you categorize, they are very complex problems. We started learning the about this optimization problems and all these things from very early stages of our school days, that like, okay, we have maxima and minima, and then to find a maxima or minima, we look for a saddle point. If the function is continuous, go for the derivative, and then the derivative is a saddle point, and then we go for a higher order derivative that gives us an idea about whether that is a maxima or minimum. And then we try to find out the iterative way of solving it. You can see in this figure here, which is basically, you can call it hill climbing approach. So we start from one point, find out the gradient, and keep on adding and keep on moving until we reach at the top. And then this works fine, but then people come out with a more complex problem, and then they conclude, like if you see this figure, they conclude here that if I start from this side and keep on finding the gradient, keep on moving, and then I'll stop here and I'll say this is the peak. Whereas if I start from this side, okay, then we keep on moving, and then somewhere here we say that this is the peak. So now it's the problem is same, but depending upon where we are starting, that makes a difference. If the for such type of problem, these are multimodal problems, multi-minima problems, and just now you can think of these figures here. You can see here there are so many minimas all across the figure, and your global minima somewhere in between, which is difficult if you go by these approaches. So now we are introduced to another thing which is known as a local and global, that can be referred from this figure here. So we can have, you can see, if we are seeing this vicinity, then we have one minima, and which is basically here, this is local minima. Whereas if I take whole of the feasible region, so global minima is somewhere here, and likewise. So these are the some definitions, and because the landscaping is important, just to understand that how many minimas are there and what is the feature there. And this is this figure because this is what we are working on. You can see here we have local and we have global settings there. Problem can be differentiable, cannot be differentiable. And if you check the benchmark problems, you can see the landscaping. So benchmark problems, you can see a bit more flat here, but you can see very peaky global minima in this figure. You can see there are a lot of minimas surfaces. In this first one, you can see it's a flat surface, so you can say it's a kind of a smooth surface, but there is a minima somewhere, and likewise. So so you can see the surface and all these issues, and then issues with the variables and all these things that put attracts the researchers to think of a different way of solving the things, and they uh, rely more on the search-based approaches. So we just search it. Okay, we and search-based means we start from somewhere, we have certain point, and we know that point is a feasible point, so we just calculate the value, and then we adopt certain kind of a policy to move. So when then we move, and then we search, then we move, then we find another solution, we check this solution is better than the earlier or not, and likewise. So you can see here at the top you will find the methods like here, and here you can see at the bottom, this is the complexity. So we have linear search, then we can have brute force search. So we search is basically we divide it into two part, and then we search it here, then divide it into again two part, and search here, and likewise. This is another method, but this one is a low level of complexity. Then grid search, those who are working in machine learning, it's a very common uh, commonly used in that applications. A grid search means you start from some point and you move into a certain kind of a pattern like this. So you move into a grid kind of arrangement, and every point, all these blue points which you can see on your screen, all these points are solutions. But our job is to find out what is the best solution. So these are the feasible solution, but we need to find out what is the most optimal one. Then a bit more complex is breadth first search. That is, you are searching along the breadth like this one. Search like along these points. Then we have depth first. So that means first we go by the depth of the network, and then we search in the other zones there. Then iterative deepening search, uniform cost search, best first search. These are the moderate complex algorithms. We go for beam search, then A star search, very popularly used in robotics, and then more on the random side, that is Monte Carlo, taboo search, and likewise. So you can see all these methods are search method, and you can see what they are giving. They are giving that, okay, we are starting from certain point. Okay, any figure you can take, we are starting from certain point, and then how to move to the next point, we get the solution, then move to the next point, get a solution, and likewise. And then at the end, we find out what is the best solution. So these are the such techniques which are being used in various domains. There are some more, like this one is crime scene search method. Okay, so you can move like searching like this. This is one kind of a pattern. You can search your landscape like this also. This is another way of searching. You can do the search in this spiral kind of pattern, or you can follow this kind of a search method, or what you can do, you divide whole of your zone, whole of your search space or feasible region into certain zone, and then you search in these zones there. This one is also search, it's an iterative gradient based, but this is also one way of searching it. We start from here, and then we find out the gradient here, and then we update it, reach to the next point, we evaluate it, then find out the gradient, and then likewise we reach to the next one. And then we have different types of methods of finding the gradient. Okay, we can have a simple gradient, stochastic gradient, but all these are if you go by iterative way of solving it, not going for one shot solutions, these are can be put into that kind of a category. Okay, so these are the few things there. These are optimization methods people have used. Okay, so even you can see this one is a simple gradient method. It's the optimization process. It's a gradient descent. So you start from some point, keep on finding the gradient till you reach to the stable solution. Even this one is also having a such kind of version, which is the simplest one, which is the first algorithm which we learned somewhere in class 8, that is solving the problem with the graphical method, linear problem. So we start from 0 0 and then we follow a method that, okay, go to the uh, nearest node, evaluate it here, then go to the next node, evaluate it here, go to the next node, evaluate it here, and then you can close it. And out of this, you can see 4 nodes, one of them is the solution. Similarly, this one is another way of solving it. Kind of a setup there. If there is a unimodal, okay, so we have arrangements. These are the two limits. So we start at the boundary, and it is being said that it's a unimodal. So where is the solution? What? So we evaluate it here, we evaluate it here, and then we take a midpoint of it, and then we evaluate it here. So say this one and this one, they are the better solutions. So then we take a midpoint again, evaluate it, and if say this one and this one is better, then again we take a midpoint over it, and likewise we convert it to a solution. So there are other such methods like you can say golden section method, Fibonacci series method, and all those methods. They come under this category. All these are optimization techniques. So when you summarize it, this is very good uh, snapshot I've taken from a research article, and this is a general structure of all the algorithms. Okay, three things are there when we talk about any optimization algorithm. The first one is how you are starting your algorithm. That is the way of starting it. Second is how you are updating your position, and third one is basically then where how you are stopping it. You'll find these three things everywhere. You can see here, you can see in all these algorithms how you are starting, from where you are starting. So this is starting point here, this is the starting point here, this is the starting. All these algorithms, they are starting point, and this starting point is there in the meta-heuristic algorithms also. We'll see when we talk about meta-heuristics, we'll see we try to understand the meta-heuristic algorithm on these 3 points there. And then the second point is how to move. So here in this algorithm, the movement is based upon the gradient. Here in this algorithm, movement is based upon this value, calculating half of the values, evaluating them. Moving here is a policy like we go to the nearest corner point. So that is basically a policy how to move from one point to another point. All these are the different policies, gradient descent, or momentum gradient, or you can use neural network, whatever. This is a method to move from one point to another. And then the last one is how you stop your algorithm. That's the stopping criteria. Just remember these three things. We'll discuss these three things when we discuss the algorithms there. So meta-heuristic is basically abstractions from some other concept, and that is basically combining those algorithms. Is started long back in 1986, and there are certain reasons, certain theories. Uh, there are theories uh, just to justify or satisfy uh, that these algorithms are more inspired from the nature. Uh, there are theories which satisfy that they are in a position, or they are able to, these algorithms are able to find better solutions. And then there are certain kind of proofing near around, like one proof is there that these algorithms are better in solving rather than going by the conventional one. Like you can see the conventional, just to serve 15 customers, the number of possible solutions are 88 billion. And if my computer take 1 million solutions per second, we need somewhere around 24 hours. And this is just a 15 customer problem, but if you think of 1000 customer problem and all these things, you need a lot and lot of computing, and likewise. So people thought of like, okay, why not to uh, uh, think of some other solutions which are which are better in a way, like we can have multiple solutions and from there can we extract something out of it. So the classification is done on various forms when we talk about meta heuristic. Where one classification is your meta heuristic. Okay, meta heuristic can be inspired from nature or non-nature. So like if I say nature is all genetic algorithm, ant colony, grave wolf, cuckoo search, and likewise. The second one is non-nature, like iterative local search or taboo search, as kind of this thing. Or we can we can divide these algorithms on the basis of objective type. In one case, the objective is static. In second one, it is a dynamic objective. Or the third categorization can be like based upon the memory. So we are using past memories like we use in Uncolony and Tableau. They are memoryless algorithms. And then the direction of search in some algorithms you'll find there is a single neighborhood. Most of algorithms there, but there are possibilities of multiple neighborhood also. And then how you evolve it, how you perform your search. It may be a trajectory based, it may be a population based. So trajectory based, you can see here, local search, simulated annealing, taboo search, grasp, variable neighborhood search, iterative local search. These are the trajectory based. And the population based, you talk about, you can these are all the algorithms like EP, ES, genetic, ant colony, particle swarm, honey bee, DE. All these are population based approaches. Okay, let's understand these two method, and now we put all those 3 points which we have started, which we to take it like the points to discuss on. So the first thing is how to start. So just check this whole region. This whole region which is there on your screen. This region is basically all these green points are feasible solutions. They are the solutions of this problem, of any problem, but one of them is the most optimal, and our job is to find out the optimal. So the starting point here is you just select randomly any point there, and so that is the S0. So that is the starting point. Okay, and then what we can do is we can decide one distance, and then in that region what are other points. So say here I have 1 2 3 4 5 points are there. So we evaluate at all these 5 points and check it out which one is the best among them. And then we choose that one as the next target, that is S1. So that is the policy here to move from S0 to S1. That is the point number 2. And then we keep on moving like this, and that will give us a trajectory. These are the trajectory based method, and the problem is there. Okay, so the problem is very obvious. Say this region which is there here, it may not be covered under those circles, radius and likewise. And maybe here we have better solutions. So this can be one of the issue. And then another one is how far we keep on moving like that. So there are certain issues with this one, and then people try to find out a solution for it. The another approach is basic. There are trajectory methods, and then there are certain kind of a possible way of doing it. So local search, one is local search. What we can do is we take any point here. You can see here the first figure. Take any point here, and then we decide the neighborhood. That these are the two neighborhood points, and then we evaluate any point in the neighborhood. And if the solution is better, then we move to that new point, and then we decide again the neighborhood. And then if the solution is uh, there, which is better, then we go there. And but now you can see on your figure that this point is whatever point you choose in the neighborhood, that is basically on the higher side, and I'm looking for minima. So that means we are trapped here, and that is basically the, we call it cell trap in the local minima. And then people worked on that how to come out of these traps. So there are various ways to uh, uh, escape from the local minima. Either you can try with different solutions, or you can change the landscape of the problem with certain assumptions, or you accept some non-improving neighbors and likewise. And then you can further divide it. You can go for multiple local search, you can go for iterative local search, When we talk about the change in the landscaping, then you can go for variable neighborhood kind of settings, or noisy methods are there. And then if you want to accept the neighborhoods which are not program code, there are other methods also there. But there is a game basically, and this, if this whole, you can put it here. You can either, what you can do is, if you're getting some solutions, good solutions, let me change the, so you can intensify your search. You search in a small region, and if you're not getting good solutions, so you can say you can diversify. So then that's the point, like you keep on moving in and out so that you can find out a better solution. This is one of the way of escaping the local limit. There are various ways. You can use perturbation method. Okay, you are trapped here, and then apply certain kind of a perturbation so that it jump out of it in this direction or this direction. And likewise, so if it is trapped here, then you again use a perturbation method. And likewise, there are many perturbation methods which help to come out of the local traps. This one is variable neighborhood, so you can have many locals there, and then they share the information. Okay, so there's a trap in one, there is a trap in another, there is another one. You shake it, use perturbation so that it come out, goes to another neighborhood, and likewise. So these are the methods which are basically people have used. So variable neighborhood method was proposed in 1997, and then later on some part of it people are using to develop their meta heuristic algorithms and all that. The second category is your population based method, which is again very simple. This one is very simple, like okay, we take some population of it, okay, and then what we can do is we evaluate it, keep some best of it, okay, discard the worst, and then take another set of population. And likewise, so this one is a population based method, where we take some population, we evaluate, and then what we can do is we keep the best one, disregard or throw away the old one, and or we modify that one in certain kind of a pattern there. So idea is to get the new points, and like so all these are the population based methods, so where we are using population as one factor. So now we have some idea of the two approaches, two broad categories, population and trajectory based. But the thing is, now talk about all, how we can uh, understand these meta heuristic algorithms. The philosophies are different, but how they fit in on those three parameters, and what are the thing people have adopted. So the first one is the genetic algorithm, very popular algorithm. Lot of, you can see the research articles being published. It is being used in various domain, inspired from the genetics, human genetics. So if we try to evaluate it on those 3 points, so the first point is how to start. Here the starting is the random, so randomly some population is generated. This is a population based approach, so randomly some population is generated. The second is how to move from one point to the another. Here the movement is governed by the genetic behavior that is inspired from that particular part. And what is there, there are three operators. Again, yesterday we have discussed the same way: crossover, mutation, and natural selection. uh, I'm sure you have already gone through this algorithm. So the algorithm is, the idea here is that this algorithm help us in movement from one point to another. So we have one set of population, you can see here, okay, one set of population, and then we follow this process which give us a new set of population. So that is moving from one place to another place. That is the idea here. And then the last point is the stopping criteria. So stopping criteria can be, depends on you. You say that, okay, run this algorithm 5,000 times iterations and then stop. That is one of the stopping criteria. Or you can say, okay, if my last 10 solutions are in this band, stop it. That's another stopping criteria. Or you can put some other condition which, if your algorithm fulfill, stop, and then it will stop there. So that's the idea here. And obviously there are parameters which need to be addressed here, Here we have crossover probability and mutation probability, and then people worked on those things so that how to get those values, those settings in an appropriate manner so that we can have better solution. The another algorithm which we discussed yesterday, that is basically differential evolution, and here the things are almost same. Again, it is a population based. The movement here is now no more just combining only the crossover between the two one. The movement here is decided by 3 different points here, rather 4 different points. The target one, we select one to combine and then crossover with third one. So there are 4 points which play a role here. But again, this operation which is there in front of you, like we take a difference of these two here and then scale deep up and then do the kind of update this one and then perform the crossover and then go for selection. So this one is the method to move from original points to the new points. So this one is the new point and this one is the original population. This is the policy, and the stopping criteria, again, you can choose it. You can put certain condition that, okay, if you fulfill this condition, you stop it, other keep on calculating the things. So that is basically what is being done in differential evolution. The next one, a very simple algorithm to understand, which is more inspired from the swarms. We can say that in genetic and DE, we are basically a more greedy one, because those who are fit, they survive, rest, die out. In particle swarm, it's different kind of a scenario that it can be greedy, it can be non-greedy, but most of them are non-greedy in the nature, inspired from the swarms, how the swarm behave. How so so then the algorithm starts randomly. You can see in the first figure, all red points, they are black points, they are randomly directed and randomly they start, and then they need to update, and they update on the basis of this equation. This equation comes from the factor when we work in a group behavior. So this one is group behavior algorithm. And in what happen in a group, when we are working in a group, then all of our decisions will be governed by the two factors. One, my own choices, and second one is my group choices. And that will help us to move from old point to a new point. And then when you reach to a new point, again we evaluate it, and then we decide what is the my personal best and what is the group best, and this process keep on working. Proposed by James Kennedy and uh, Russell in 1995. And again, starting is random. So in most of these algorithms, you'll find the start is random and end point, the stopping criteria, that is basically decided by the developer. But the middle part, that is a policy to move from, or policy to search. Move means policy to search. That is basically inspired from some species or some happenings near around us. So in PSO, that is simple here, but here you can see these are the parameters, W, C1 and C2. The search is on how to get the most optimal value of W, C1 and C2. And I'm sure Prof. Panigri discussed on that one a lot, that what are the variants people have developed, how they have played on C1 and C2 and omega and all these factors there. Okay, there's another algorithm which is basically ant colony algorithm, proposed in 1999 by Dorico, and here the method is a bit again, the starting point is same way. We have some nodes and randomly we can start it, but the policy is decided by how the ants move, how the ants behave in the nature. So some experiments have been made, like here you can see and here you can see. Uh, Typically ants are blind, but they follow a certain path. And the experiment done by people, that when the ants are moving, they put some obstacle, and then initially you can see the ants, they are divided on both the sides of it, but after some time they follow the path which is the shortest one. So how they do it, then the more research on that part, and they find out that there's drop a liquid and they smell it, known as a forminone, and then this forminone is a factor of your time and temperature. Now this is some research there. So materialistic algorithm, not like just like that they are happening. They are people are developing. They do a research on that how these species are behaving. They are behaving in certain fashion, and then what is the hidden thing which is there? Can we use it for our purpose? And that basically people use it to develop a policy to for the movement of all those things. So this one is ant colony, which is derived from the forminon, and then so they model the forminon properties as a function of time, and then you can see the equations here in terms of the probabilities and the function of temperature also, just to develop this algorithm. Some variants are being developed later on, but more it's suitable for more of like a TSP problems and kind of that setup. There is no, this is not a centralized processing. Then we can have different discussions. What are the good and what are the bad about the algorithm? But this is the way it will go. Then there is another algorithm which comes into the picture, that is harmony search optimization algorithm, relatively new, 2001 by Professor Kim, and this is inspired from the music. So you can see when we talk about the music is composed of certain kind of the instruments and certain kind of rules, like here do mi solo, or in Indian classical we have sare gama and all that, and then the combination of the instruments, and if they are played at a certain note, that that give us a kind of music. And we remember certain music which we listen very long when maybe we were kids, but still we remember because the harmony is good, so we remember them. Some combinations are not good, we forget after some time. So here again the music, you can say three instruments, you can take they are having three different notes. Okay, three different variables, sorry. They have certain values, and then we put it into the function, we evaluate it. So this is again they start it, and now we can have different combinations here. One combination is initialization, or you can take it from some old music. So what, some or music in some other language, and then you play near around it. That is one way of doing it. So you can have already you have certain, that is basically some start point is already we have, but then we modify near around it. We play some pitch somewhere, some frequency somewhere, so that we can have good harmony. The second maybe some memories is there, some good sound is listened somewhere, then we modify that sound, add something to it, we develop it there. And third one is randomly we can go for these things. So we can have a different way of starting this algorithm. We can have a total random, we can have some kind of fixed values there, or you can have certain kind of a memory or distribution. From there you can take it, and then you modify it. So here you modify on the basis of the two values here, HMCR and PAR. You modify your music and then update your memory and keep on calculating this thing. So this algorithm has various different ways of start, but the modification is basically on the basis of HMCR and PAR. We'll get a new harmony. We keep on updating our those things, and this algorithm works that way. This one is a directed B colony optimization. We proposed it long back in 2014. So here this one is basically not pure B, it is basically directed B. And then this is not, you can say, purely heuristic. It is a combination, it's a modified version. So I think you have heard about B. I think Professor Bansal or Professor Kusumdev, they have talked on B, but this one is a modification on that one. The idea is here, can only one property is taken. So on the B behavior, there are a lot of properties. Okay, so the property here taken is basically that is when they search and the memory, it is being, it is put some in some of the articles that bees have a memory of 4 places or likewise. So initially when I was working on it, I was thinking like how to connect it in that way that 4 positions can be taken together, and we can have a search algorithm which is basically derivative free. So this one is a geometric based search algorithm you can see on your screen, which is not new. Somewhere in 1949 or something, it was developed by Mendel method and known as NM method, which is being used to check it, how the search process can occur there. But the part here is, which is important, is it is basically a kind of a combination of deterministic and heuristic. So it's more of towards a deterministic side, and that's a good part of this algorithm because it can be applicable to real-time problem. But we have used these kind of decision making in directed B colony, which is known as consensus and quorum. So the decision is being taken on the decided, like whether you want to go by consensus and quorum, and then proofs were there just to understand how this algorithm. So the play part is basically, this is the search part. Basically, this is the search part, which is inspired more from the geometry part there, and then the decision is basically both operations of decisions, consensus and quorum. They are incorporated here to move from one point to the another point. Then there is another algorithm which is gray wolf, and then this one is gray wolf algorithm, which is inspired from the gray wolves. And you can see the wolves have a hierarchy: alpha, beta, delta, and gamma. And then alpha take a decision, and beta, delta, they help. The alpha and gamma, they are just the followers. This was the initial algorithm proposed by Mersley and the team there. We created a variant in this one, so I'm just putting the picture of both here. So variant we created, like classical one, it is believed that the movement is basically linearly decaying. This is a coefficient. If you go into the calculation of gray wolf, this A, it is taken linearly decaying. But when we watch many of the videos on the gray wolf and likewise, and in animals, it's difficult that the movement is just simple in one line. They always they go in a line, but it's not a simple line. There's some kind of a movement near around that line. So what we did here is we add a noise. So we searched various noise, and we found beta noise, giving a better result. We add beta noise, and then we modify the movement like this, and then we compared it, and we found that this change in the algorithm produced better result. This is the policy, basically policy of movement. So what is the policy of movement? This is governed by this equation. So that the distance is calculated from omega with alpha, omega with beta, omega with delta, and then the mean distance is taken, and then omega move according to that one. So this one is almost, if you go by that, this one is somewhere, if you do the mathematics and break it. So in PSO we have two distances. We try to go to close to those two distances. One distance with my personal best, the another distance with the global best. In gray wolf, there are three distances: distance with alpha, beta, and delta, and the omega try to move in such a way that it moves near to all of them, and likewise. So that's the policy here. That is how it will work. And then there is another algorithm, which is whale optimization algorithm. And now you can see here what is the equations are almost same, which you can see in gray wolf. But again, this algorithm is proposed by Mersley and his team. But the search mechanism is now, it's a spiral in between. Okay, so the earlier in gray wolf, the movement is like this. It's a linearly going towards the prey, but here some probability is added. So if you are in values more than the probability, you go by this. If you are less than this probability, you go by this, and like so. This is the algorithm, but there is a justification. It's not just like that. The justification is basically, if you go and watch the discovery videos, you will find this one. The bubble net is there, and the bubble net formation is a spiral formation, and that inspired them to add spiral to it and to develop this algorithm. Similarly, then there is a edge spider monkey algorithm. This one is improvised version on spider monkey algorithm. Spider monkey algorithm was proposed by Professor Bansal and his team. We put a aging effect into it. Okay, so you can see there are various leaders where there are various phases. This is a bit more interesting. Spider monkey policy to move from one point to the another point is basically it works on the fission and fusion structure. But in what we did in SMO, there are 6 phases. First phase, they search for local leader. Then there is a global leader phase, and then local leader learning phase, global leader learning phase, and then local leader decision phase, and global leader decision phase. You can consider this one is more like a government system where there's a central government and there are state government, and likewise. What we did here is we when we searched a lot on this behavior, we find that there is a certain kind of observations on the old monkeys and the baby monkeys, because their behavior is different. They are not their behavior is not as same as the rest of the monkeys. So what we did is we cluster them as a child groups. Okay, and then we after clustering them, then we add the behavior of the children and the mixing. So we add age as a factor, and what is how it is doing. So number of iterations can be taken as a counter in the age, and this algorithm is modified. We proposed in 2016. Okay, then there is another algorithm that we proposed very recently in 2023. And this algorithm is from Seven Sister Optimization algorithm. You have seen these Seven Sister, uh, there are different names to it. In some reason they are known as Seven Sister, in some reason they are known as Seven Brothers. Basically, they are jungle bubblers. They make a lot of noise and then keep on jumping, and then they search the food. So the algorithm is basically the starting point is now they are 7 in number, somewhere around that. So that there are 7 starting points, you can take it. And then the algorithm is basically when they search it 7 start point, then then one of them will be the best. But then the policy is to move. So how to move it, and and how to do that searching. So searching is basically they search near around in a random fashion. We tried various kind of distributions there. So some distribution we have presented in this paper, that how to use that distribution part. There is a one observer who observe the motion. So in this paper, initial paper, we have taken a Brownian motion based on the Gaussian distribution. The equation, if you see it, because this one is also group behavior activity, the equation is almost, you can see a similar kind of PSO, but the behavior of the searching near around and all that is a different, and that we published in 2023. So just 2 year old, working more on that kind of a domain. Okay, so that is basically, I'm now going towards the end of this, because then we have 5 minutes or so for the question and answer. So I think we can take another algorithm, which is intelligent water droplet, proposed by Ahmed Hosseini and team in 2009. This is inspired from the formation of a river and droplets. So this one is more like okay, I'll talk on the queries later on. So the this algorithm is more on like how the droplets they move. So you can see that droplets in the hilly areas, when the river formation take place, they are small, they are very fast, and then water is muddy. But when they move, so they carry more sand with them. But when they carry sand, then they become heavy, they settle down, and in the plains you will see the water is more clear, the sand settle down there. So this is like the how the things are happening in the natural process, that is considered here. So in hilly region we have more speed of the droplets, in plain region we have less speed, and this approach they have used it, and it is more like a path kind of a structure, trajectory kind of the algorithm. This policies they have used it to work on getting the new solutions or moving from one point to another point. Similarly, there is a Firefly algorithm, which was proposed in some 2009. And the Firefly algorithm, what is the way, what is the policy to move? So we know that Firefly generate light and they are attracted towards light. So once they have better solutions, it is assumed that there are more light, and then more firefly move in that direction. You can fix the direction, and then accordingly you can take a movement from one point to another. You can see in the literature there are a lot of variants like discrete firefly, multi-objective firefly, Lagrangian firefly, chaotic firefly, parallel firefly. These are the variants people have developed. But the policy to move from one point to another is basically the intensity of the light which is being there. So you can model the intensity of light by certain function. The good algorithm is, if you are modeling that behavior, modeling the behavior what is happening in the nature, uh, then your model must be as close as to the actual happening. If it is so, we can say that okay, this one is a good nature inspired algorithm. And likewise, simulated is similarly another algorithm which inspired from your cooling property. So they have used the cooling property and cooling behavior to move from one point to another point. Similarly, we have fish schooling method, which is basically how the fish, when they're small fish, then they combine to get safe from large fishes, or they go for a food there. Similarly, there's a BAT algorithm proposed by Professor Yen Shi, and then basically that is how the BAT behaviors, bat take the movements and see the prey and food. This is more on the part that they generate certain kind of frequency uh, frequencies, and then they receive it, and based upon that they identify where is the uh, where is the obstacle or where is the food, and likewise that is being taken as a policy to move from one point to another. You can see in the equation 6 and 7. And then you can see a lot of variants are there, like people have used fuzzy logic in that one, they have used k-mean algorithm, they binarize it, they use a differential operator also, because they have these Levy flights. So they, how the flight is being taken, and then they use certain kind of combinations there. Similarly, a cuckoo search algorithm is there, which is again by Yang and team. So has they, and they introduced this one, and the inspiration is taken from the cuckoo, because the important part is how cuckoo lay the eggs, where it lay the egg, what is that location. That is basically the best location for a cuckoo, and then how the eggs being fetched and all those processes. So that is basically the policy here in the cuckoo search algorithm. Then there is another one algorithm which earlier become very popular. Still a lot of variants people have developed, proposed by Simon in 2008, known as a biogeography based optimization, inspired from that, like how the species they migrate from one point to another. So it is basically immigration and emigration, and that is somewhere related to like okay, kind of how the birds, how the various species they are reaching to the solution particular island, or how they are moving out of the island. And this kind of arrangement is being used to understand the habitat behavior. So this is more on the understanding or inspired from the habitat behavior, and being used as a policy to uh, move the various values. Bacterial foraging is very popular. Uh, I don't, I can see, because there is a bit more complexity in the cal mathematics. Uh, People worked on it, but became not that popular because of mathematics. But this is very good algorithm proposed by Kevin Ampasino in 2002. This is basically E. coli bacteria, which is there in a body, and then the interesting part is how it moves. So it has various part, it rotate and the swing, and those are the controlling factor, which uh, you can say are the key factors to to move from one point to another point. So it swim and then it rotate. So how it rotate clockwise and anti-clockwise, and that is being used to develop this kind of algorithm. Okay, so then that's all here for today. I think I am in time. A lot of other algorithms can be evaluated on these parameters, uh, like how your things are happening. So, but if you are interested in, check the 3 points there. First, understand which species you want to work on. Do a in-depth analysis of that one. Study about the animal psychology, physiology, behavior analysis, and then check on these 3 points: that how to start your algorithm, what is the policy with that species or that particular thing which you want to model, how that is behaving, and then how to stop your algorithm. Probably you can come out with a new algorithm, and once you are happy with your algorithm, then there are benchmark problems, there are CEC problems. Go and work on the CEC problem. Check it. People have already published. Check it out. How many models your problem is or your algorithm is performing better. If it is doing good, it's nice. If not, then I think then we have certain thing in our hand, and that is how to tune the parameter of the model you are proposing. Work on those. Maybe your algorithm is good for engineering problem, not for some other setup. Maybe your unimodal may not be a multimodal, maybe on multimodal, or may not be on certain kind of aspect. But these are the things which you can use it to develop a new algorithm. Uh, and now if you have any questions, please post it or unmute it. Then and then we can have discussion. So there's a one question from VSD, that justification for 7, because justification is just only that we call it a 7 sister, so they are usually in the group of 7. So that is the only justification, that, and that's why they are known as 7 sister or 7 brother birds. So that's the idea, to start with 7 sister. Like in GWO, it is taken as like the size of the group, whole group is somewhere around 10 to 15, not more than that. So they usually we go for that. You can increase and decrease it, because that, for us, when we are working on optimization, it's a simple variable. So again it will be a point of agenda later on, that what should be the good number of the starting search point, because we have seen yesterday in DE many people have worked on what should be the optimal value of NP, the starting point, and likewise. So is there any paper saying that this algorithm is chosen on what type of data? Oh, dear, you will find a lot of discussions there. Even people have put a lot of blogs there, that which type of algorithm is performing better, which type of for. I have shown you one screenshot which was very old yesterday, that if my problem objective function is linear or non-linear, my variables are integer or they are non-integer, and then what I want to solve, then which algorithm is good for it. So then you can check on these things. You can check on this kind of analysis. People are posting it, because every day you'll find new algorithms are coming, and people are comparing it and then proving that this algorithm is performing good on these parameters. It's not like it's all are good. Like I can say DVC, which I propose, that is good on one factor, and that factor is basically the deviation is not there. So mean and standard deviation not there. That means you run it 10 times, it will give you the same result. Reason being, it's a geometry based. Starting point is fixed and geometry lengths are fixed. So it will reach to almost, it will, most of time it will go to the same solution. Maybe agenda of research is maybe trapped somewhere. Nobody knows, because if you explore more on it, you can have a better idea. Sir, could you suggest a best suited algorithm for a reservoir operation in the context of hydropower? Right now, Mohan, Mr. Mohan, it's difficult to say, because I don't know the mathematics of your reservoir operation and hydropower generation and irrigation supply. because you can formulate the problem in many ways. Let me share you a few very interesting thing. There are few problems. We have also published on those one. Those are electrical engineering problem, and people that is PMU placement, if I'm not wrong. And then people implemented a lot of meta heuristic on that one because it's a placement problem. And then somewhere around 2000, I think, if I'm not wrong, 10 or something, there's one paper came in by Professor Abid, and then he put the formulation in a different way, and the problem changes from materialistic to a simple kind of a simple integer programming kind of setup there, and then people stop working. So this is how you are formulating a problem. You need to understand how you are formulating. It may be sometimes better that your problem you formulate a problem which serves your objective, and it's a simple problem. Don't worry on that one. It's not always necessary to implement meta-heuristic everywhere. Meta-heuristic is good when your problems are very complex, but if you are able to formulate a problem which is simple and we satisfy your requirement, I think that's the best kind of a thing you can report it. I would like to know why particle swarm optimization or genetic algorithm got combined with Firefly theory. See, these are the combination, Sakshi, because people keep on trying. Each algorithm, some algorithm has some kind of a good, something or bad part, but sometimes to me it looks very strange. I have seen many papers that they use one algorithm and then another algorithm, both are meta-heuristic, and then they combine, and then they say that a novel meta-heuristic algorithm. It's a basically hybridization. One algorithm you use it for certain purpose, maybe for initial feed, maybe fine-tuning the parameters of the other algorithm. You can use it. Okay, so these are just the combinations people are trying, because when we model anything, we have certain parameters which has to be optimally tuned. Only in that case our model is okay. So if say PSO you are working on, so now you have three parameters to be tuned, your C1, C2 and omega. You don't know. So okay, to me it looks that okay, GWO is easy. So what I can do is I can use GWO to tune your C1, C2 and omega, and then you use that PSO for solving a problem. People are doing it. They are just trying to redefine the things or trying to find out the better solutions. Sir, if you are continuous in decision make variable and control variables and real value parameter, what algorithm? So if everything is continuous is known to you, and you know uh, what type of the landscape you have. If it is unimodal, if it is a continuous, you can use any continuous derivative because it's a non-linear. You can use any kind of a non-linear method. Issue occurs if it is a continuous. First issue, and it is multimodal, and you don't, and then it's so many minimas are there, multi-minima kind of problem. There can be a issue. You cannot use the conventional one. People either they modify the landscape, then they use it, or you can go for meta-heuristic. Or if it is non-differentiable, then obviously you have to go for some approach where we cannot apply the differential approaches. Again, a question is that how can Firefly algorithm can be related to wind energy applications? So you can do it. One, if you are modeling the wind energy generation, say you are using just one example. Say you are using a prediction model, okay, to predict the wind energy. So that is you are doing it by neural network. So I need to find out the weights of the neural network. So instead of using back propagation, I can use Firefly to find out the weights. One way of doing it. Another way, I can use Firefly uh, to to choose the number of which model is good for me. So I have four models. I have one model which is say logarithmic prediction model. Another one is decision prediction model. There are then decision tree prediction model. Another one is another prediction model. So out of this, which one is doing good for me? So there are various ways, various kind of setups where you can use this Firefly algorithm for wind energy production. You can use it for modeling, you can use it for tuning, you can use it for feature reduction, you can use it for new model development also. Okay, there is another question is, sir, can you kindly give a best suited algorithm for microgrid operation and optimization? Again, Vivek, the question is very relevant, but the point is how you want to control your microgrid. What are the components of your microgrid? Whether your components are linear or components, whether your components are non-linear, whether your components are hybrid, combination of linear and non-linear, whether you are looking for only operational, that is 0-1 operation, or you are looking for operation with the values, or you are using data-driven models also into it. It totally depends upon what is your problem, and based upon that we can make a call that okay, this algorithm is good or this is not there. Okay, so another question is, can I combine TLBO with PSO for hybridization? You can do it, but my suggestion is, rather than doing it, apply some good mathematics to find the tuning parameters, rather than you just combine TLBO with PSO. Because if you stuck up in such kind of a combination, then there are n number of combinations, and maybe somewhere you yourself not convinced that either to the reviewers also or the examiners also, that what is the reason why you are getting better result if you combine TLBO and PSO. So better is you use TLBO and work on the parameters of TLBO, try to find or use on PSO, work on the parameters of PSO, modify your PSO parameter with some strategy. Like one is like, you know, PSO, emotion based PSO. So some kind of logic there, where you can say that where you can claim that I have tried this kind of behavior in group, and then from that behavior mathematics I developing this thing. So that is the good way to do it. Any more questions? So there is hybrid more multiple resources. How to write the time complexity? Yes, this one is a totally different domain. Mr. Rajshekhar P has asked a very good question. For that, we need to see the how you are writing each and everything, because not only this, you have to find out. Now people are asking, because when people are combining it, that's why people are asking, write down the time complexity with notation also, and give us the time convergence, time calculations also. And for that, friend, you need to go for the algorithmic book. There's some notations. When you are writing a code, see if you are writing from that notation, check on, and finally you can conclude what type of big O notations you are taking, or some other kind of time notation techniques you are adopting it. But this is very important, and my suggestion to all who are going to propose a new algorithm or using these algorithms to write down their problem, please add one extra table there, that the your algorithm, your time complexity is this much. This will add on, this will give a good flavor to your article and have a very good chance of acceptance. Okay, again, the algorithm is suitable optimization decision making at mobile devices. Okay, if you're solving mobile devices, then there are different problems there. But if you want to run on your mobile device, then the thing is, take that algorithm which is having the lowest time and space complexity, because that will consume less power and will consume less space. So that you have to see that which algorithm, even few of the search algorithms have shown you from the low complexity towards higher complexity. You have to see that what is that algorithm which is having the lowest space complexity or space requirement, as well as taking a less time to converse. Any more questions?
Thank you, sir. You have answered all the queries raised by the participants. Uh, I request you to say. I request you to share the slides after it, so that it will be passed on to the participants.
Yeah. I'll put it. I'll share these slides very soon. with you also, and I'll put very soon on my website also so that they can download it
Sure.
for their purpose.
Sure.
There is a question like algorithm for determining the phase quantification. Okay, you can use some kind of a machine learning if you are having a good set of the data to quantify your material. So if you have a lot of data, experimental data for with you, you can use any kind of machine learning or AI or data science approach to quantify your materials. And to fine tune those models, you can use optimization technique. Yes, okay. No more questions now. So thank you, Dr. Eli Sharma and
Dr. Elijah. Yeah.
Dr. Nanda.
Yes, sir.
Yeah, namaskar, and for giving me this opportunity to share a few of the things. Probably next time we can see someone who's listening today come with the new metaheuristic algorithms and put it here that okay, we have to develop this new algorithm and now you can use it. So thank you very much. Thank you, everyone.
Thank you, sir. Thanks.